So I'll say a couple words. So Noel has a very big crowd because Noel has been an integral part of the lab, and I'd say Caltech for his whole time here, as again evidenced by all the support he has here. He started in as a hands-on roboticist, so that's the background. And early on made stuff like walk really quickly, and then went into the theory deep dive, right? Phase, which he now come out of with layered architectures. So it's been rewarding seeing the development process. It's awesome seeing the videos, and looking forward to the presentation and seeing what you do at Figure and making humanoids do fun stuff. So with that, take it away.
Thanks very much. Yeah, I'll switch this off. Just all right. All right. Thank you. Thank you. Yeah. All right. So you'll see the slide number at the bottom right. We have like a lot of slides to get through, so I'll try to not dwell on things. So thanks everybody for coming. I'm excited to talk to you about hierarchical control and walking robots, and maybe why now is a good time to be thinking about their combination. So I wanted to start by kind of painting the scene of when I entered the lab, even in 2016. This is what was state of the art. So okay, this is 1980s. This is before my time, but still, I think it's state of the art. This is MIT Leg Lab, a hopping robot we have running at Michigan, and then walking and 3D walking on Duris. This is a video that inspired me to join the lab, actually, or one of them. And I wanted to point something out. So the question of this era, kind of when I started my PhD, is how do we get dynamic stability? So how do we leverage the dynamics of the systems? But there's another thing I want to point out, which is each of these robots are custom and different. And so in order to do research in the field of legged robotics, you had to design and build a custom robot, and then you had to design a controller in order to publish it. So that was a lot of work. So now I want to contrast this to kind of where we are. These are like within the last year robot demos. And they're pretty crazy. So we have a lot more capability. But you see they're walking, they're running, they're kind of dancing and playing. And this is, yeah, that spinning was crazy up there. You see that? This has captured the interest of entrepreneurs. So in the last 2 years or something, there's 20 plus humanoid companies that are starting. And the question has changed. Instead of just getting dynamic behavior or achieving a task, the question is does this have product viability? Can we achieve something useful? And so now we start to ask systems level questions instead of just individual behavior level questions. So here's the problem setting we're going to specialize to. I want to input some semantic query, complete some task. And we're in the business of designing controllers. So we have to produce some policy which gives a torque to the system. That's a huge span to jump. So I'm going to leverage something by Animesh Garg. I saw this at ICRA in London. And he allows me to separate what we want to do and how we're trying to do it. So what we want to do is kind of an environment. You're requesting a change in the environment. So I want to move the cup over there. And that's independent of the robot morphology of how you're trying to do it. And so what we are interested in is how we actually, given, let's say, a goal state and an environment representation, how we realize a torque that gets the system to do that. So we're going to leverage what most roboticists know, is that spanning that level from a goal state to a torque is already quite large. So we're going to split the problem into subcomponents. Namely, we're going to leverage different levels of a hierarchy, each which has independent focus. And there's a few benefits for this. I'll just touch on some briefly, and we'll kind of, it'll be a recurring theme. So I can leverage different models. So I have an idea of model separation. And also I can plan them at different time scales. And this is natural for the two levels of abstraction. So let's specialize this idea of a hierarchy to our problem setting. And let's try to do constructive synthesis. So instead of just saying abstractly how we should split the problem up, we want to actually design controllers that achieve a task. So that's what we're going to do. So I'm going to put some specifications down. I'm saying I have a goal state. Let's say I want to get to the green circle. And I have an environment representation. Let's say these are obstacles. I want to be able to reach arbitrary goal states. I want to avoid the obstacles. And I want to satisfy the input constraints. And that's very easy to write down. But it's very hard if you're in robotics to actually solve. So luckily, we can translate this mathematically exactly. So if I write down the mathematical expression for these, I can write down an optimal control problem that will produce a solution to this problem. But there's an issue with this, and I have these are hard constraints that I'd like to do, and these are maybe 3 soft constraints that will guide the philosophy of controller design. I'd like it to be real-time capable. I'd like to have some notion that it's going to work, and I'd like it to be applicable to many different systems, not just one system. And so solving this altogether represents the idea of kind of a monolithic solution. And what we'd like to do instead is split the problem, as I said, into, let's say, a high level and a low level, and have an interaction. And this is going to achieve all the things that we set out to do. So what we'll notice here is that in each of these levels, we're solving an optimal control problem, which is a transcription of the task that we want. So I wanted to go a little bit into solution philosophies for optimal control problem, not because I want to do one last lecture, even though I'd like to do that, but because it'll motivate kind of the philosophy of what's coming later. So this is the pendulum, the phase portrait. If you know what you're looking at, then you know. If you don't, it's OK. These are the natural dynamics for the pendulum. So let's say I want to stabilize to the origin. This is a naturally unstable point. So one strategy I could employ is I'm going to globally solve everywhere in the state space for a feedback strategy. So this is great because once I've produced this, I can just query, I'm at a point, what's the vector field I should apply? By the way, side commentary, control is the art of designing vector fields. So when we're shaping vector fields, that's really what we're doing. So it's fast to evaluate, but there's a notion of rigidity associated with this. So if I produce a global solution once, let's say I add a state constraint, so avoid this part of the state space. I have very little insight about how to change the underlying vector field to adapt to this new constraint. So this is maybe the philosophy of Hamilton, Jacobi-Bellman, or RL, or something like this, which is baking in a global solution. Now, there's a different solution philosophy, which is I can start from an initial condition and only plan a path that achieves the goal from where I need it. So this is what I'm calling a local planner. Now, if I impose the same state constraint, I can just update the plan, because I'm only producing it where I need it, and I can reevaluate that. So there's a notion of flexibility associated with these. But there's also a notion of fragility. So if I only plan one path and then try to track it, there's numerical discretization error, all this stuff. If I just play the torque feed forward, then it might not track very well, and it might diverge. So there's a notion of fragility. So instead, we are going to see a combination of planners and trackers, which balance this speed and flexibility trade-off. But if I just have so anyways, roboticists know this, right? But if I just have a unidirectional information flow, so I plan a behavior and then try to track it, now if I impose the same state constraint, the planner, which is the blue line, thinks that it's satisfying the state constraint. But because I have some uncertainty in what I can track, I might violate the state constraint. So the argument here is that we really need information flow going both directions in our hierarchy, both up and down, so that the planner can accommodate solutions, and we get this idea of guaranteed feasibility. So actually, I made this last night because I realized that John Doyle was right. So there are levels and layers. There are. As much as I wanted to resist it. So as we saw, there's going to be high levels, there's going to be low levels, and in each there's going to be planners and trackers. And so kind of the thesis statement, pardon the pun, and we'll come to this at the end again, is that by having bidirectional information flow in this layered architecture, we enable exactly what we set out to do, the soft constraints. Besides solving the problem, we also get efficiency, feasibility, and generalizability. And we see in the speed flexibility trade-off curve, these layered architectures enable something better than each independent layer. All right, so the outline for the rest of the talk, this was kind of the philosophical take. We are going to try to instantiate all of these individual pieces for the hopping robot, for the videos that you saw at the beginning, for the task of path planning. So we're going to start at the low-level tracking layer. So why is producing a tracking controller for a legged system hard? Right? I know where I want to be. Let's say I'm producing a plan from the planning layer. Just track it. So there's a couple of challenges. Here's the fundamental one. So these are all legged systems. There's a quadruped, a planar biped, and a hopping robot. These are all ones I've worked on in my PhD. And so I'd say there's kind of 4 critical challenges. There's long, highly underactuated phases. So as I said with the hopping robot, I don't have a torque at the center of mass state. So when I'm in the air, I'm just following a ballistic trajectory. It makes it hard to converge to a desired center of mass state if I don't have a control input. They're relatively large dimensionality. So just already in 3D, I get a lot of degrees of freedom. They have these hybrid nonlinear dynamics and then manifold valued states. So we're going to address all of these challenges in the design of planners and trackers for legged robots. So I want to hone in on underactuation. And this is going to be, we're about to commence on a large discussion of underactuation, because this has really been a critical piece that I've tried to understand during my PhD. So let's start with a walking robot. Here's a state space representation. I've got joint angles, joint velocities. Here's my dynamics. So the issue with underactuation, as I said, is that I have a rank deficient matrix. So my control input is not affecting all of the states that I want it to. So if I look at this, I've got motors on the hips and the knees, and I can converge those to kind of what I want them to be doing, but I don't have a motor on the center of mass state. So I see this as like a point contact foot, so it's falling like a pendulum forward. So let's start with these. So we're trying to develop a tracker. We know, this is just a brief thing, but if I have a desired trajectory for the knees and hips, I can readily design feedback controllers that converge these to the outputs to the desired behavior. So let's see what this looks like for the systems of interest. So here we've got the planar biped. I'm just specifying, let's say sinusoids on the knees and hips. This is what you should be doing. I have this for the quadruped, and then for the hopping robot, I say stay upright. So OK, we're getting some kind of motion. This is a first pass. They're in the air, so they're not actually achieving anything that we want. But let's go from there. So is this the whole picture, right? And I want to make a claim, or not a claim, but an observation, that this is only a subspace of the state space because we have a rank deficient matrix. There's actually a whole other set of coordinates that we need to think about in order to understand what the system is doing. So this is the unactuated state of the robot. So here, as I said, the center of mass state is the unactuated state. So what's convenient about this decomposition is that there is a direct mapping between my state space and the coordination of the actuated coordinates and the unactuated coordinates. So before, when I was just looking at the actuated coordinates, it was not enough to claim anything about what the full system was doing. But now I have the full picture. And so as I design desired trajectories for my actuated coordinates, I have to think about how they are influencing the states where I don't have actuation, right? As I move the knees and hips, it's going to move my center of mass state, through the dynamics, but it's not going to directly impact them. So kind of a large premise of what we're trying to do is that if I have exponential stability in both the actuated coordinates, so we knew how to design controllers that stabilize the actuated coordinates, and also I have exponential stability in the unactuated coordinates, then because of this bijection, I can state something about stability of the overall system, which is really what we're interested in. So this is just a lens for analysis that we're going to leverage. So now the question is, right, we know we can design desired trajectories. How do we design trajectories for the actuated states that stabilize the unactuated states? OK, so this brings us into the next phase. We know that for the actuated coordinates, we can track them exactly, or we can track them. And then now we're trying to plan trajectories that stabilize the unactuated states. So we're going to return to this optimal control problem. And we are going to leverage this idea called model predictive control, which is an online method for doing trajectory optimization. So here is the hopper flying through the air. How do I stabilize the system, or how do I produce a trajectory that's stabilizing? Well, I'll forecast the dynamics into the future, see where the hopper will end up. I'll optimize what my current action should be in order to get stability over the horizon. I'll apply that control action, and then I'll replan. So this is giving me a notion of feedback. So let's solve this problem. So we're doing constructive synthesis. It's not enough to say that there is a solution to this problem. We have to actually find the solution. OK, so we have to address these challenges. We can't just avoid them. So the long, highly underactuated phases, actually the claim is that the replanning of this system with MPC stabilizes the full system state. So let's keep that in mind, but let's avoid it for now. Relatively large dimensionality, so modern solvers are actually powerful. So because we're not doing global solutions, we're doing local solutions with MPC. We only have to plan over trajectories. And so we can actually do this, but also keep this in mind for later. OK, so there's two remaining things that we have to deal with in order to solve this problem. So we have these hybrid nonlinear dynamics and the manifold valued states. So let's start with the dynamics. So what does this look like? So if I write a mathematical model down for what the system is doing, it starts in the air, where it has this flight phase, continuous time dynamics. And then it impacts the ground. And we can model this as a discrete impulse event. And then it flows in the ground phase. So when the spring is compressed, another continuous phase. it hits the hard stops, another discrete impact, and then it flies in the air. So there's an issue with this. Well, first of all, it's nonlinear. And second, there's a discontinuity. So often when we solve optimal control problems, we're going to rely on gradients to produce solutions. But this discontinuity is going to be an issue for when we produce gradients of our solution. So how do we get around that? Well, how do we get around the nonlinearity? We are going to linearize about a reference trajectory. How do we get around the discrete event? We are going to fix a contact schedule. So I have a reference, and whenever the reference is going to make contact, that's when I'm going to I'm going to optimize over the states that do that as well. We can have a long discussion about whether that's a good idea or not afterwards. But so that is a continuous time system, continuous time linear system. And then I'm going to, because we have solvers, they need to be in discrete time. So I need to discretize the system state as well. And so this is kind of a sequential quadratic programming approach to solving model predictive control problems. OK, great. So that's the hybrid nonlinear dynamics. Now we have to deal with the manifold valued states. So the orientation for the hopping robot, that's specialized to this, can be modeled as a unit quaternion. OK, so that's a Lie group, which is a manifold. And then we have an associated Lie algebra, which is a vector space. So what's the issue with manifold valued states? Well, if I do this approximate linearization and discretization and produce paths, I might end up not satisfy. These are all approximate, so I might not satisfy the manifold valued state. So I might produce an orientation that does not satisfy like a unit norm constraint, let's say. So it's not a valid orientation. So we're going to propose a change of coordinates. So let's start. Let's say I have a manifold valued trajectory. This is what I'm trying to track. And I know I have the identity element and the associated vector space. So I need to be able to pull this manifold valued state back into a vector space, because I know how to do Taylor approximations. I know what to do in a vector space. So let's start by doing a change of coordinates. I'm going to pull that trajectory back to the origin. And then I'm going to apply the log map. So this is a local bijection between what's called the Lie algebra, which is the vector space, and the Lie group, which is the manifold. And so now I can plan over values in this vector space. I can take Taylor approximations here. And so we've essentially been able to figure out a way to deal with these manifold valued states. So I'll just show it up quickly. Basically, we've transcribed this continuous time nonlinear problem into a discrete time linear problem. And we're planning over the Lie algebra, so this vector valued states. OK, so let's see where we are. Let's rise up, see how far we've come. Is this work? So these are the natural dynamics of the hopper. So if I were to just drop the hopper, that's what it would do. OK. So let's see now when we add this idea of model predictive control, so producing trajectories on the fly to stabilize and then tracking them, what behavior we get. So this is the first hopping we got on the hopping robot. And you can't hear it in the video, but I'm basically screaming for success. I was so excited when this actually hopped. And so we see it's able to kind of stay around. And then it falls over eventually. And we're going to come back to that in a little bit. So it doesn't hop very high. Maybe you'd like it to hop 6 feet in the air like Disney or something. And so we can, in simulation, just switch the torque limits off. And we can see kind of, is this a limitation of our method or of the hardware? And as a control engineer, you can always say, oh, it's the hardware's fault. So here we're able to see very large disturbances. It's reorienting itself in order to stabilize. It's planning over the horizon. And so I'll let this play out at the very end. There's a cool behavior. So here it's doing trajectory tracking. The red circle on the ground is where we would like the system to be. And the yellow dots, you can see it's planning over the horizon. This is where it's predicting the center of mass is going to be. And so we're able to track this kind of square trajectory. So now, right, we're kind of abstracted away the dynamic stabilization, and we're thinking about tracking. And then here, it's well, just a second. OK, there we go. Everybody loves a flip. And then they say, when is it going to flip on hardware? And I say, never. So OK. So OK, here's another point. First of all, I want to when we pushed the robot, you saw it took a large step to stabilize itself. So again, it's leveraging the actuated coordinates to get stability in these unactuated coordinates. But the real commentary I want to make about this result is that this is the same model predictive control philosophy applied to a new robot. Okay, we didn't change, besides the implementation details. Basically, it's the same philosophy. You're doing MPC and you're tracking, and it's extensible. We can apply this same thing to a new system. So this is one of the powers of hierarchies. And so we have it on hardware. Just quickly, it's going to walk across So this is meant to be a planar biped, so I had to put wheels on the gantry to get it to walk, and I don't want to know what happens after the video ends. Okay. Okay, so let's kind of resurface a little bit. Where are we? We have talked about the tracking layer. We've talked about the planning layer for these legged robots. And I'm sure you want to be done with the planning layer. You'd like to move on to the high level. But we're not quite done yet. So I'm going to dwell on this point a little bit more. We're about to go into another deep dive about underactuation. So I don't want to say I cheated, but maybe I omitted some details here. So this hopping robot had a Wi-Fi module, and I was doing all of the compute on board a very powerful desktop. And so I was planning, there's optimal control problems when I said it's high dimensional, but solvers are powerful. Well, solvers are powerful, but the compute on board is very limited. It only has an ORIN and some teensies, and I have a huge CPU. So we were leveraging the fact that we could just communicate off board and do all the planning on an external computer. And then for Amber, it was connected over Ethernet. So we're thinking, I want to put this on board. And here's the real question. And this was, I would say, really the crux of my PhD, is asking this question. Does underactuation necessitate online replanning? Is there something fundamental about an underactuated system where I have to do all this expensive compute online to forecast trajectories? And really, this question bothered me. So this is whiteboards of math of trying to answer this question or think about how to actually find solutions to this. So I'm going to save you all the effort that I went through, and I'll give you the answer. The answer is no. So how not if we saw that we needed to do that in the past? Well, let's go into it. So let's instead solve this problem once offline. So do a trajectory optimization once instead of the online replanning. Okay, but there's an issue. I said if I solve it once and then try to track it, then I have this issue of not having feedback. I might just diverge the system state. So what does this look like on the hardware? So you'll see I walk, and then it falls over. So we're missing a notion of feedback. So the sentiment here is that tracking the time-varying solution, so I have this, it produces a desired trajectory. I put it through my mapping to the actuated coordinates. I drive the error to 0 in time. It's not enough. Okay? So instead, we need to add feedback. We know we can add feedback on the actuated coordinates already. So what we need is feedback with respect to the underactuated state. So this is not something that I developed, but this is inspiration for what's coming next. This is in the line of hybrid zero dynamics theory. So what we're going to do is we're going to map the underactuated state to an interval, 0, 1, and then we're going to modulate the desired trajectory by how much progress we're making in this underactuated coordinate. So this is giving us feedback with respect to the underactuated state. Okay, so how well does this work? So this is not doing, okay, there we go. It's not doing any online planning. It did offline trajectory optimization once, and it's doing this remapping on the underactuated state online. And it's really good for this planar biped. I mean, the MPC, it kind of just beelined across the room, and some of the results were a little bit, yeah, I'll show you at the end. But this one is extremely robust. It's robust to different treadmill speeds. You can push it. It works on different robot morphologies. So here we have just point contact. Here we have spring legs. And so we'd like to do exactly this, but for our hopping robot. So what's the issue? Well, so here's the issue. So basically, we were taking our underactuated state. We were mapping it into an interval, and then we were modulating the desired trajectory by that state. So we were trying to take our underactuated state. So for the planar biped, that was just the center of mass of the hip. The center of mass, position over the foot. And we were trying to map that into this interval, like I said. But the issue for 3D is that now I've got two states of underactuation. I've got x, y positions, also velocities if you want to incorporate those. But just a simple dimensionality argument says that I can't produce this bijective mapping between or from this two-dimensional space to this interval 0 to 1. So we can't produce this phasing variable like we want in 3D. And also, another limitation that we'd like to address is it's restricted to these periodic behaviors. So we have to go, in order to make this work, we have to go through a trajectory. Okay? So can we relax this? Can we generalize this or extend this? So what we're going to do is instead of going from the underactuated space into an interval through a trajectory, we are going to just produce a mapping from the unactuated state into what the actuated coordinates should be. It's kind of a simple philosophy. It's inspired by reduced order models. based on what your center of mass is doing, tell me what my foot should be doing. OK, so what we're looking for is we are looking for this mapping such that when I drive the system to what I want it to be doing, so if I say, OK, your legs are exactly where you wanted them to be, you need two properties. You need to satisfy invariance of the zeroing manifold and stability of the manifold. So stability of the manifold, we saw we can get with optimal control. So we're just going to solve this discrete time optimal control problem. And invariance, we're going to say, let's start with an initial condition on the manifold. Let's apply the discrete jump, so the impact to the ground. Let's flow it forward under the dynamics of the optimal dynamics and see if we land back on the manifold. So we see that instead of solving for a single trajectory, right, what we want to be doing, we're solving for an entire subspace of optimal actions. And also, instead of focusing on the continuous time, we're focusing on the impact of the continuous time as it pertains to the discrete time, which is one way, that's the predominant way that you get stability for these legged robots. So the issue is that we're no longer doing trajectory optimization. We're trying to solve for a spatial function. But conveniently, this can be expressed as a loss function. So we're going to try to learn of mapping psi, which satisfies the invariance and the stability. And if I put those two together, here's the discrete update. I want to know that if I take the optimal control action, I land back on the manifold. That's just what this expression is saying. OK, that's a good idea, I think. So what does this look like? How do we actually do this? So in order to do this procedure, step 0 is to implement optimal control in a differentiable simulator. So this is like an implementation detail, but I wanted to include it because this is a non-trivial task in order to get this to work. And we had a lot of challenges, actually, with doing this, because differentiable simulators these days are still in beta. But let's say you've done that. So what is the procedure? I'm going to sample my underactuated state uniformly at impact. So I want to dwell on this for a second. So you could imagine another way to phrase what this idea is you want to imitation learn trajectory optimization or imitation learn optimal control. In order to do that, you'd have to collect a large data set of states. So this is a large dimensional system. I'd have to do, I'd have to sample uniformly and try to figure out a policy that does what I want it to do. But what we're saying here is by leveraging the structure that exists in the system, we know we can do tracking on the actuated coordinate. So we're leveraging only the thing that's complex, which is what the actuated coordinate is doing as a function of the underactuated coordinate. So I'm going to sample the underactuated coordinate at impact. I'm going to evaluate what the policy is telling me to do. So that's going to give me an impact angle. I'm going to solve the optimal control problem and see where I ended up and see if I evaluate the policy at that new underactuated state, how different is that from what the optimal control action was telling me to do? That's going to be my loss function, and I'll backpropagate. So if I get to 0 loss, it means that I have a policy that is telling me to do exactly what optimal control would do, but it's only doing it on this low-dimensional subspace. OK, how well does this work? So these are the videos you saw at the beginning. These are my favorite results from my PhD. So I'm going to just let these videos play and then maybe talk over them if I have something to say. Actually, this is a good opportunity to get some water. So no, actually, I'm going to go to the next one, and the next one, cool. So this is blind traversal. This is just kind of, let's say, proprioceptive feedback. So it's measuring kind of what its orientation is, what its center of mass state is, and it's doing this coordination. Oops. Well, let's go to the next one then. Of, based on what the center of mass is doing, you should tell me what the orientation you want the system to be is. And then I can just take that and do PD control or some other stabilizing controller to that desired orientation. So this is completely blind. It's just going upstairs. This is a disturbance. You saw I have a joystick, so I'm not precise. It's like an Xbox controller, actually. It's pretty thrilling to drive this around. It's able to go up the ramp. You saw this at the beginning, but I guess I'll just let it play down the ramp. OK. Sometimes the friction coefficient gave out and it slipped, but this is a good video where it didn't. OK, here's another result just to show kind of the precise tracking. So this is a 2x4 that's 3 feet off the ground. And we just commanded it to go to the other side of the 2x4. And actually, this worked 3 times in a row, but the first 2 times I didn't know how to convert inches to meters. And so it stopped right here and looked like it didn't complete the task. So, OK, here's my favorite one, too. So watch this. Watch this. Oh, that's beautiful. Look at that. So, I mean, look, it's based on how I disturb it, it's saying what the actuated coordinate should be doing. It says I need to impact at that large angle in order to stabilize my system. And it requires no online planning. This is a neural network that's just evaluating to tell my system what to do. And this was enabled because we thought about the structure and we leveraged the hierarchy that was underlying. Yeah, cool. OK. OK, now we can take a deep breath. We've gotten through the low level. So now we're on to kind of planning questions. So high level, we still, yeah, my hopping robot can reject me kicking it. That's great, but it still can't go anywhere without me joysticking it around. So what have we done? What has this gained us? So if I wanted to do planning on the full system state, we talked about how complicated it was. It's got hybrid dynamics. It's high dimensional. But because we have this block that's able to stabilize the system, we can kind of ignore a lot of the complexities of it. And instead, we can just think about, this is a top-down view of the hopper. We can just think about what the center of mass is doing. So now we can design what we want the center of mass to be doing, how we want it to navigate through the space. And so we can just kind of forget about a lot of the details for the system. OK, so what's coming next? So let's consider an integrator system. So this is just the center of mass state, a double integrator. That's what we're going to do planning on. So the goal of this section now, I have my hopping robot, right? I want it, instead of just going straight, I have an obstacle representation. I want it to avoid the obstacles and get to the goal location. So I can, again, just write this down directly as a trajectory optimization problem. It's a very powerful language for which we can express these tasks. But if you think about how to actually solve this problem, there's an immediate complexity, which is that the state space where I'm trying to stay in is not convex. So non-convexity prevents this from operating in real time. So there's a lot of current research on how to solve these mixed integer non-convex problems. But let's take a different approach for how to do this. If instead you could give me convex regions to remain within, then I have a convex problem. And I know I can solve this quickly online. So if I know that this curve should stay kind of approximately in this set, then it doesn't have to worry about whether to go left or right or how to deal with this non-convex space. It just focuses on producing a smooth curve. OK, so this is the philosophy of the planner and tracker at the high level. I mix levels and layers up. I'm still trying to get it set in my head. High level. So here we are still dealing with the tracker. And the planner will be some sort of discrete graph solve. But in order for the discrete graph solve to be well posed as a warm start for this solution, we need a valid abstraction of what we can track or what we can achieve at the tracking level, tracking layer. OK, so the next question is, how do we abstract what we can track? So we're going to leverage kind of this very pretty curve called the Bezier curve. So it is just this product of a basis polynomial. So these are like convex interpolators and my control points. So what I'll do, if I evaluate this between 0 and 1, it's the same interval 0 to 1 as before, but that's just anyways, we don't have to dwell on that. It interpolates between these control points. So let's say this is the initial condition, this is the terminal condition, and it's going between it's just interpolating between the points. OK, so let's think about this. Basically, I have boundary conditions. I have an initial condition. I have a terminal condition. And I have, let's say, a convex state constraint. So again, I'm assuming I have some sort of convex state constraint. And I have a box input constraint. And I want to know, how do I produce curves that satisfy these constraints? So this is not a good example of a curve, because you can see, even though I'm trying to reach a point that's inside the convex constraint, the continuous time curve is exiting this set. So that's bad, because that means it's hitting a wall or something. And so as I trace the boundary, we see that sometimes the curve stays within, and sometimes it violates. So we're trying to come up with a representation of endpoints that we can reach such that it stays inside the constraint set. So there's actually a pretty cool result, which I worked on. So you can leverage some properties of Bezier curves, namely that they're linear in velocities and other, they have other linearity properties, and they satisfy this convex hull property. So I know the continuous time curve is contained in the convex hull of the control points. And then I know that the set of terminal conditions that I can reach with a Bezier curve, which satisfies these constraints, is just given by a convex polytope. And I get this directly. It doesn't require compute or anything. I don't have to do backwards reachability. OK, so how does this help us? Well, let's say I ignore this. And I just try to get to a point that's across the room. I don't think about what's achievable. I just try to directly plan a curve. We can see that the system just is way too aggressive and it falls over. So instead, if I leverage this idea of what's reachable by the tracking system when I'm doing planning, it produces, it's kind of hard to see, but it produces this sequence of points that eventually reaches the goal. And it's able to keep the system upright. OK, so that's the tracking layer. So the final piece of the puzzle, we're almost there, is to talk about how we plan. So we haven't discussed how to deal with the non-convexity of the state space yet. So that's the last piece. OK, so here is the planning layer. So we're going to build a graph of these Bezier curves that are connected exactly when they're reachable with one another. So we're going to leverage what the tracker can do in order to build this graph. That means that if I find a path in the graph, I know that the tracker can track it. So once I've produced a graph without obstacles, I'm going to cut the graph based on where the obstacles are in order to get edges that are collision-free. So I can solve, if I want to know if a Bezier curve is in collision with an obstacle, this is just a feasibility constraint. I have two convex sets. I want to know if there's a feasible point that's in the intersection of the convex sets. So you can write this as an LP feasibility check. I used a QP because there's good QP solvers. The issue is because I have millions of edge obstacle pairs, this does not terminate. We can write it down, but if we think about actually solving it, it was not fast enough. So there's this heuristic we can use. So if I have a Bezier curve, and if any of the control points are inside the convex obstacle, I know that the curve is going to hit the obstacle, so cut it. If all of the control points lie on a separating hyperplane from the convex obstacle, then I know that it's collision-free, and so I can keep it. And otherwise, it's indeterminate, and you have to do this expensive check. What's nice about this also is this is just set membership checking. And so I can put this directly on a GPU. So GPUs are kind of particular about what you can and can't do. So I can't do the QP check directly, at least yet, on a GPU, but I can do the set membership check, and it's fast. So let's compare. We run this heuristic on a CPU. It runs in 6 seconds for this complicated, long horizon task for planning. So that's not real-time feasible. We run it on a parallel CPU. It runs in, I parallelize the threads to try to do the collision checking. It runs in 3.5 seconds, still not real-time feasible. Implement it on GPU, and now we get 70 milliseconds. Now it's real-time feasible. This is leveraging, not just expressing the problem, but thinking about how we solve it and the structure that is there. OK, so once we, oh, sure, yeah. Oh, that's an excellent question. Yeah, so the big bottleneck there was copying the memory between the CPU and the GPU. But if we look at the videos, it works in real time, so it's sufficiently fast. And what's actually convenient about doing it onboard the Orin is the Orin has shared memory between CPU and GPU. So that was really cool to realize. OK, thanks. Yeah, but that's great. I mean, yeah, that's the huge bottleneck with putting things on GPU. OK, so I can solve. Once I have a collision, I have a graph that has no obstacles, I can solve for a path where just the edge length is just some upper bound of the edge lengths of the Bezier curves. And I know that this discrete path, because it's a graph of Bezier curves, can be converted into a continuous time path. And then finally, I can pass that down to the tracker, and the tracker can just remain in these convex corridors and close to the set, or close to the path. OK, so what does this look like? So this is the scale of problems that we were trying to solve to test the method. And this is why it didn't work on the CPU directly, because there's a lot of edge obstacle pairs. So here's the hopper right there. That's the goal location right there. And then we can see the cyan is the graph solve. That's the solution. And then the dark blue is the refinement. It's doing a local smoothing of the curve. So I'm going to let it play. So because we did this, we thought about compute, we can update the plan online. So as I change the obstacles, this is just randomly seeding it with graphs, it's able to replan paths faster than you can. and then I speed it up just to show that it actually gets there in the end. Okay, so we're going to also do this on hardware. So we have an overhead camera that's segmenting where the obstacles are. I've got a graph representation. It's producing this graph, and then it's smoothing with MPC. And I'm leveraging the fact that I have a good tracking controller which can realize this Bezier curve. So I don't have to do this non-convex high-dimensional path planning, but instead I can just do it on a simplified space. So you see we added an obstacle. It's segmented by the camera. And instead of following the same path that it did, now it has to go the long way around. Okay, I want to show that this works online too. So in real time, as I kick this obstacle, you can see that the hopper kind of adapts where it's going to go. Well, maybe I don't kick it in its way. There we go. So it goes kind of around it. So this is working in real time as well. So I'll just maybe let these play a little bit longer. For a different, okay. Oh, there we go. Good kick. Now it has to go around. Oh, I'm messing with it, so it has to keep going the long way. Okay. We can resurface once again. So this is the complete picture for the hopper. So in the abstract and kind of in the thesis, I talked about wanting constructive methods at each level and each layer. So we really took a deep dive into how to produce elements at each component. And so what does this leverage us? Well, here's the final demo. You might have seen me taking this robot outside around campus. We can put it all on board. So now it's got onboard compute. There's no secret Wi-Fi external computer. It's got onboard vision to do state estimation. And this is it hopping in place and going left and right. Yeah, onboard. There's no warrant on board. It's behind this little, I'll show you later, but there's a 3D printed little shell that it's tucked behind. Okay, and then here's the final demo. So let's see if I can match the speed of it showing up. So here's the environment. We threw down random obstacles, whatever we could find. And then we segmented it. We clicked on where the obstacles were, and we gave it a free space representation. We produce this set of convex sets, the collection of convex sets of where the free space is. We cut the edges that are not inside these free spaces. We solve a graph plan. And then this is the closed loop trajectory. So we can see that we are tracking it. Not exactly, but we're buffering the obstacles by how much we can't track. And so we have this notion of a guaranteed feasibility. So I know that it's going to be collision free. So let's see if we have the patience to let it play to the end. I might skip it. But you should believe me that it gets all the way over there. Okay, it's going to get past the curve and then we can stop. Okay, there we go. I did a path planning around the curve. Great. Okay, so back to the thesis statement of the thesis. So we have these levels and layers, this hierarchical solution. And so hopefully I've conveyed to you that by splitting the problem up and coordinating, we're able to enable efficient, feasible, and generalizable solutions for these complicated tasks that we want robots to do. And that layered architectures balance this speed and flexibility trade-off very well to give you pieces that are better than, or give you solutions that are better than any of the individual pieces. Okay, so I guess I'll go through this last part sort of quickly, but I talked about some of the pros. I would say there's 3 more pros. I know this doesn't look like a balanced table, but so one of them is fighting dogmatism. So if I think that my method is better than somebody else's method, if I've abstracted away what that method should be doing, you can just evaluate a metric of how well it performed. And then you can say, well, actually, this is better because it satisfied the metric, right? Instead of producing a black box solution of, look, this is better and you can't beat it. It can also be used as a design tool. So this is actually how we came up with the high level planning stuff was, okay, I have a tracking controller. I'd like to do path planning. I know what the input-output structure should be. How do I design a component that's able to do that? And then also it gives me a separation of tasks. So besides efficiency, I can have 2 different people working on problems, and I know that when they come together, I have an expectation that it should work. So I want to mention maybe some cons of the philosophy. So this is the Cantor set, which I'm using to represent the aerospace industry. So hierarchies themselves can become ingrained. So if I have this infinite splitting of subtasks, and I say, okay, now I have this really challenging problem, and I've produced this individual block, and all you can do in order to make progress is update this one block, then maybe you're resistant to large-scale changes that would have better solutions. Another take is that splitting the tasks is suboptimal. So if I were to produce a global solution of optimal control, let's say this is the feasible solution space, right? By splitting it and coordinating, I'm trying to impose nice structure in the solution space. And so this gives me an optimality gap. But the argument is kind of like what you give up in optimality, you gain in a lot of different pros. Okay, so we'll go through these quickly, but I have a few soapboxes that I'd like to get on. So the first thing is about ethics of robotics. And so we're arguing that we should produce general solutions for robotic systems, but that does not abstract us away from their applications. So we should really think about, by proposing general solutions, let's say militarization, automation, et cetera, there are impacts to working on that. Okay, AI, this is my definition of AI. I've worked pretty hard on this. So I think AI is a completely subjective term, meaning anything beyond the understanding of the person using it. So I have a toaster, I put in bread, I press a button, and every time it gives me toast. So it must know what toast is. It's intelligent. Okay, anyway, so basically all AI for robotic systems is really, there's architectures and there's control, and we should call it what it is so we can analyze its behaviors. Okay, performance maximization. So all of these robots that I showed at the beginning, they're doing really cool dancing and flipping and all this kind of stuff. But we forget that there's a fundamental trade-off between performance and reliability. And if I look at the systems that are actually deployed, they're not as flashy, but they work really well. And so as we're trying to get the coolest robot demo, we're kind of limiting the reliability of the system. And so if we want to get these systems to do things that are useful, we should really think about where on this curve we need to be. And then this kind of reminds me, I guess, John Doyle would have liked this talk, I guess. So this reminds me, as, let's say, LQG regulators pushing performance, and they forgot about reliability. This is a, required reading for your PhD in controls. There's an abstract, 3 words, there are none. Yeah. And I think you could make the same thing about black box controllers. Okay, and then hardware, I could go on and on about hardware, but I think this picture summarizes my experience with hardware. All right, so here's the papers that I've worked on. So I only talked about, let's say, the top 7. So there's a whole other thing that didn't really fit in the arc, but it's in my thesis if you want to read it. Okay, I have some blooper reels. So this is Amber doing online trajectory optimization planning, and it kind of has a mind of its own. Yeah. This is like 2 a.m. in the lab. Yeah, hardware, right? Okay, so here, you think the hopping robot is free from bloopers. It's not. It didn't see the obstacle. Its state estimation went invalid. The foot stopped working. And then maybe this one will work. Oh. Just kidding. The state estimation went invalid again. All right, so those are the bloopers. Okay, so we're talking, we're in the acknowledgments thank you section. So obviously, thank you to the committee for being here and for all the guidance you've given me, different office hour visits and everything. Yeah, I'm grateful for all your feedback. I didn't practice this part, so let's see what I say. Yeah. I also want to say a huge thank you to the admins, Michaela, also Lynn, but especially Michaela. I mean, the lab would not function without you. You've been a huge help smoothing the time here and helping with everything. So thanks so much for that. Okay, well, I have to give a special thank you to my advisor, Aaron Ames. So this is me. This is the lab at Georgia Tech. So I don't know, yeah, you probably remember, but we've known each other for almost 10 years now. It's been a long time. And so, as you said, I started just doing machining. I was interested generally in robotics. And I'm just extremely grateful for the opportunity you've given me to go through the arc of going from somebody who's machining blocks in a shop to thinking about controller synthesis and kind of, being able to ask these questions at this level. So thank you. Here are some pictures of lab. I've had a lot of fun in lab, and I think it's good to keep light spirits even as you're there at 2 in the morning trying to push for a deadline. these are egocentric, so I'll skip that. I don't want to acknowledge myself. I just thought they were funny and I needed to include them. Lab would not be the same without all of the wonderful lab mates that I've been able to share it with. And so I really value the group and the sentiment that we have together. And so thank you for everybody who's been in the lab and I've shared time with. There's life outside of lab. And so for all the friends that are here and other friends, thank you so much for the experiences we've had together, kind of exploring this wonderful nature out here in the Southwest. So exploring, traversing nature in different ways. Obviously to my family, so my parents are here. So this is, I thought I would woo you with some young pictures of me. So, yeah, so grandmother, grandfather, another grandmother, uncle. So, I wanted to show this. So this is my dad controlling a spot robot, which I never thought would happen. He's a linguist, And so maybe that's a commentary on how ready these robotic systems are for deployment. All right. Thank you to Hannah. These are some pictures of us. And Kaio the dog, yeah. Yeah, you've helped me keep my sanity. And thank you for enduring some of the late nights in lab and for all the adventures and stuff we've been on. So I'm looking forward to what comes next. And then lastly, I guess, these are some pictures from the mountains. So really, the mountains have been my refuge in grad school. Like I said, there's great nature in the Southwest. Some of these are the Sierras. And so I've had a wonderful time exploring nature and also working in lab. Okay, that's it. Thanks. Yeah, you want a mic or? Okay. Uh-huh. Can you discuss the last what you discussed in that paper? Yeah, sure. I guess I won't go to the slide, but okay, the question, if you can't hear over Zoom, was how does that work compared to graph of convex sets? Russ Tedrake, all the people in this lab are thinking about that. So the first one, which was like cutting the graph, was not explicitly producing a convex set representation. So we thought about using graph of convex sets, but it requires first inflating a bunch of convex cells in my entire state space. And then what's nice about that is you can relax the problem, but get a pretty close to optimal solution. So instead, we said, I'm not going to think about the convex sets. I'm going to leverage a graph solution. So I'll produce the graph first. And then I'll cut the graph and I'll solve the graph. And then after I have the graph solved, I only need to produce convex sets that are along the path. So there's a computational trade-off. Basically, Iris, I couldn't find a good open source plugin for Iris, so that's why we developed that one. But yeah, we can talk more about some of the parallels. Yeah. Yeah.
So you made the statement that online replanning was not necessary for underactuated systems.
Right.
But there was still like a horizon-based planner somewhere in the stack, even if that was distilled down into a policy.
Right.
Would you agree with the claim that for an underactuated system, somewhere in their stack, there has to be a horizon?
Okay, yeah, so a horizon is necessary in some form, but you can either do a planning-based solution, right, like local strategies of shooting forward trajectories, or you can do kind of a global feedback strategy. And so the reason you need a horizon is because your inputs don't affect your system state right now. So you need to leverage the dynamics over a horizon. You need to reason about that. But it's true. I mean, it's basically where you draw the line about what it means to have a horizon or not. And so I would say maybe the question stated a different way is like, do I need to do online trajectory optimization, or can I distill that down and do that instead? And maybe this is the philosophy of RL as well, something like that. So yeah. Yeah.
You talked a lot in the videos about like how proud you were with like doing different things. And you also talked a ton about how many like mathematical hurdles you kind of had to hump, and there were so many different like challenges. Was there a particular one that you're like real proud of, that you're like, oh my gosh, I finally got over this? Even in the simulation, you're like, wow, I figured this out.
Oh yeah, I see. I'm making eyes. Hold on. I'll answer this The demo, the reason I liked that result so much was not just because it had cool hardware. It had cool theory. And the fact that those came together, we had a notion, like a proof that this should work. We leveraged learning, and then we had a cool robot demo. I mean, it just all came together. And so that paper is the one I'm most proud of in the entire PhD. Not just the video, but the whole concept. Yeah. All right, well, I think we're getting kicked out of the room. So thanks, everybody. Yeah, we do. It's 3:20.
Okay, so for the committee, up in room 320, everyone else go about your day.